Hey friends, MoNaCo here. Our fourth lecture in acid-base unit. We're actually going to talk about the good old-fashioned Arrhenius theory of acids. It's an important theory that you do have to know because this theory is used to classify the behavior of compounds as either acid or base. So let's get into some notes here. So is there more than one way to look at the behavior of an acid and base? Of course, there's more than one way to look at it. We chemists so far have just told you about acids having H out front and acid in the name, and bases having OH in the end, having OH in their form, and base and hydroxide in the name, pardon me, and that they neutralize. So let's look at some behavior at the atomic level as to what's actually going on with acids and bases. And this is a theory. Arrhenius acids define a substance whose water solution contains or yields hydronium ions, H+, as the only positive ion in solution. That's the foundation of Arrhenius theory. H+ is what acids produce. Acid makes H+, called hydronium. That is Arrhenius theory. Now, examples. HCl makes H+ aqueous and Cl negative. H2SO4 makes two H's and an SO4. So strong acids dissociate 100%. And dissociate means to break into the positive ion and to the negative ion. Strong acids dissociate 100% water to produce H+ and whatever else negative. Now, general rule for acids, hydrogen is the first ion in the formula. It's always a positive ion. Not all substances that contain hydrogen are acids, though. Below is a list of hydrogen compounds that do not dissociate, so non-examples of acids. Water, it's neutral. It's the product of an acid and a base. Methane, see how the H is in there, but it's at the end. Hydrogen peroxide, ammonia, and glucose. Methane also. These have hydrogen in them, but they are not considered acids because they do not produce the H+ ion when they're put in solution. So when you see a hydrogen ion becoming an hydrogen atom becoming an ion, it loses in electrons. Thus, positive ion is essentially a proton. When in water, this H+ ion actually is attracted to the unshared electrons and slight negative charge of that polar water molecule. And it's believed that we've created an H3O+ ion. So when an acid loses an H+, that H+ kind of comes around and finds the water molecule to make H3O+. That's the hydronium ion. According to Arrhenius, the properties of acids are functions of these concentrations, because if this way we say that H+ is H3O+. Yeah. That is technically a coordinate covalent bond that the hydrogen ion attracts to the water molecule. Rare, but sometimes mentioned coordinate covalent bond. Either way, different types of Arrhenius acids. There's monoprotic acids. Those give up one hydrogen ion or one hydronium ion. If you make one, HCl is one of those things. It makes H+ and Cl negative when it dissociates. There are diprotic acids. There's two hydrogens that come off of these guys. Typically, these happens in two steps. They're usually stronger than monoprotic acids because they pack twice the punch. H2SO4 in the first step, it becomes HSO4 plus an H+. And then the second part, that becomes SO4, and it was a negative, SO4 negative 2, and another hydrogen. Either way, two hydrogens can come off. Diprotic, 2. Di, 2. Mono, 1. Guess what the next one's going to be? Triprotic. 3 H+ ions can dissociate in 3 steps. So it goes H3PO4 to H2PO4 negative plus an H+. Then it goes to HPO4 negative 2 and another H+. And then it goes to PO4 negative 3 and a third H+. All of these are considered hydronium. ions. They will attract to a water molecule like so, to create the coordinate covalent bond, and what you will see sometimes as H3O plus. All of those things mean the same thing. Acids put off H pluses, which could be called hydronium ions. They coordinate covalent bond to water molecules to make H3O plus ions, according to Arrhenius theory. Arrhenius base, opposite of an Arrhenius acid, but it's defined as a substance whose water contains OH as the only negative ion, in solution. Examples, we've seen many bases so far. They all have OH in them. General rule, it contains OH at the end of the formula. Been saying that all along. One exception is NH3. Why, may you ask? Because monohydroxy base, mono 1, produce one OH in aqueous solution in a single step. So we get K plus and OH negative. Dihydroxys produce 2, Ca plus 2, and OH, 2 OH negatives. And then the trihydroxy bases produce 3, so we get an Al plus 3 and 3 OHs. I know I did just ask you why might ammonia be a base, even though it doesn't have OH in it. We're going to leave that to an alternate acid-base theory to explain. Not all compounds that contain OH are bases. For example, alcohols, organic acids are not bases. Non-examples of bases, water. So water is not an example of an acid or a base because, boom, it's neutral smack dab in the middle. Other examples, methanol or methanoic acid, they're not technically bases because the OH does not dissociate in these particular situations. Those guys have a strong hold on their OHs and they won't let them go, so they're not basic. Points of Arrhenius theory. Arrhenius acids produce that H plus, H3O plus when dissolved in water as the only positive ion. Arrhenius base produce OH negative when dissolved in water as the only negative ion. Thanks for watching.